So today I want to talk about heat and kinetic energy, potential energy, and what all of that has to do with temperature. It's also going to talk about how changes of state also can be represented by different energies and what specific latent heat is. So you might have heard of the kinetic model of matter, which can be used to describe the state's structures. For example, solids, liquids, and gases, we could say, according to the kinetic model of matter, in solids, the atoms, for example, are very closely and tightly packed together. They vibrate about a fixed position, and they all touch each other, and they are at um, a regular setting, I guess, or a regular structure. And we can also kind of extend on the kinetic model of matter to describe changes of state and energy and how that all relates to the energies of these different molecules. So let's say we have this little test tube, and inside it has this thing called octadecanoic acid, and we're going to look at the melting of octadecanoic acid. So let's say we've heated this thing up and it becomes a liquid, and when it's a liquid, it's a clear liquid, and we just let it fall. This is room temperature, so it's basically way above room temperature, maybe at like 80 degrees Celsius, and then it's gonna fall. And as time goes on, we see that its temperature doesn't fall in a linear line, it doesn't fall in a very constant kind of pattern. It actually goes through this weird thing where it decreases a bit and then it goes through a period where its temperature does not change as time goes on. And then it keeps decreasing again after that. So, what's basically happened is that over here, the octadecanoic acid has frozen. So when it has been heated as a liquid, it's basically kind of changed to the solid kind of form of itself. And then down here, it's already kind of a waxy sort of solid, so above room temperature. And that's what happens in the melting point. Now, if you want to look at the melting of octadecanoic acid, then the graph would be very different. It means we'll be supplying heat to it. So let's say at room temperature, it's like this. It's over here. And we start applying heat to it. So as time increases, the temperature of the octadecanoic acid solid at this point, right? It's a waxy solid at this point. It also increases. At its melting point, it's going to start to melt. And then it's going to start increasing again into a liquid form. So heating up the liquid form as well. So basically what I'm trying to show everyone here is, in this graph, we're basically just showing how the octadecanoic acid is freezing because it's changing from a liquid to a solid. But the main part of this is that the melting point sees a period of time where the temperature remains constant. So this was, measured using a temperature probe and a data logger. This is the temperature probe, and it leads up to a data logger. You could also do it with a thermometer. For example, this was the test tube. You could have a thermometer inside here. This bad drawing of a thermometer. So specific latent heat is the amount of heat or the energy required to change 1 kilogram of a material into another state without changing its temperature. What's happened right now is that this octadecanoic acid from a liquid state into a solid state, when it was changing, the temperature didn't change. However, it kept on giving out energy. So when you are freezing, you give out energy to the environment. It's an exothermic process. And although it kept giving out energy, and usually when we give out energy, we think that it's going to go down in temperature, it didn't, and the temperature remained the same. So we're going to talk about why that happens and how that's even possible. Let's first talk about the different energies that molecules might have inside of a substance. So let's first of all go with the easiest example possible. Let's look at a solid, and maybe these are the molecules that are in a solid, and they're actually always vibrating in a fixed position, as you've seen from the kinetic theory of matter. And what we see is that because they are always vibrating, they have kinetic energy. And it is this kinetic energy that determines their temperature. So you could also say that kinetic energy is kind of like a measure of the temperature of an object or how hot it is to our touch. And that's what determines kinetic energy. Then we have to talk about why these molecules are sticking together in the first place. Now, these molecules are sticking together because of their electrical or electrostatic attraction to each other, the chemical attraction to each other, which bounds these molecules together, these intermolecular forces. So you could also relate this with the sort of potential energy that you might have when you're on the Earth. This is the Earth, and maybe this is you. Now, when you're on the surface of the Earth, we say that you have zero potential energy. And you might have heard that because potential energy is mgh, and if height equals 0, then potential energy will be 0. Now, it follows from that idea that if you put something and you lift it upwards away from the Earth, let's say this is a ball, and maybe height is 15 meters now, 15 meters above the center of the surface of the Earth, then you would have increased your potential energy by that much. So mgh would follow. Although this is not the most accurate way of picturing gravitational potential energy, the ideology follows that if you do work against a certain force, and this is a gravitational force going inwards, if you do work against it and you bring something upwards, you give it a position, and at this position, it has the potential to fall down and make a new movement. And so that's where the word potential comes from, in potential energy. Potential energy is basically energy that an object has because of the position of that object. And because, this ball, its position above the Earth's surface gives it its energy, and it can use this energy to accelerate back towards the ground if you let go of it. So in the same way, the intermolecular forces, and if you can take a look at this photo right here, this is how it works as well. So if we take these two molecules, and let's say they're really close to each other, and this is their separation, we denote that by R. We take this and we do work against the forces because, the forces would obviously be towards each other because they have an attraction to each other. We do work against these forces, we bring it outwards. So we're basically putting energy into this. Now you can think of this in two ways. Because we did work, energy was put into this, and therefore by the theory of law of conservation of energy, it means that its energy must have had to increase. Another way of thinking about it is that just like this ball, now it has a bigger potential to kind of fall back to this molecule as close as possible, and that's why we've increased its potential energy. So main point is that the separation between these two will determine the potential energy, and the potential energy is lowest when they're sticking together and they can't move anymore. It's the highest when they're extremely far away from each other, maybe at infinity even. Another thing that might be a bit confusing for some people is that potential energy is negative. And I know that energy is scalar, so it has no direction, it's just a quantity. And the reason why we decide to make potential energy negative is because, let's say that we brought this point to maybe like distance equals, or maybe like separation equals infinity. So it's an infinite number of meters away from this, which means that the force field of this molecule right here, it no longer has an effect on this molecule. And that's why it has completely no force acting on it. And we decide that when a certain object is in that state, we give it potential energy equals 0 joules. And that makes a lot of sense because now you can kind of compare how deep is the pool of different types of molecules. And there's really nothing special about the attraction between these two molecules. Let's say these are two H2O molecules, for example. If we set two H2O molecules being together, we set that as a 0, then this is going to be different from, for example, two O2 molecules being at R equals 0 together. And that means this has to be like, for example, 0 point something something joules or negative something something joules. And it just makes the whole entire process so frisky if you decide to take a certain two molecules and then you say, oh, when they're stuck together, then let's put that as 0 joules. it makes the whole entire process for other types of molecules, for example, the different types of molecules, their calculation is so much more complicated because now you got to relate every single one of those to these random two molecules, maybe H2O molecules, for example. So we don't want to do that. Something more universal is when any two objects are at an infinite distance to each other, we decide to put that as 0 joules. And that's why this happens. So this makes a lot of sense to me. The further you get away from it, and you can see the separation R, the closer the potential energy line gets to 0. And maybe at infinity, it would touch 0. But we can't obviously show that on an actual graph, unless you're going to do it on a computer, for instance. Then we have potential energy. You can see that when separation R gets very small, the potential energy gets very, very, very negative. So you don't have to do a lot of work to separate two molecules that are already pretty far away from each other. However, at first, when they're very close to each other, you need to do a lot of work. You need to put in a lot of energy to even make a slight difference. For example, look at this. Over here, the potential energy is like maybe right here. Over here, the potential energy is around here. So you need to put this much of energy to get this much of a change in separation. And actually, I think that really makes sense because when you think about two magnets being together, you need to put in the most force when they're closer to each other, but when they're very far from each other, you barely need to put in any force to separate them even further. So I hope that makes a good idea of what potential energy is, not only for these atoms or molecules, but generally for a bunch of different things. For example, this magnetic attraction, it can also kind of be understood using the understanding of potential energy. We can also understand things like gravitational potential energy and the different ways in which the solar system works. And we can understand it partly using this understanding of potential energy. So I hope that helps a lot. Then we say that the electrical potential energy of atoms is negative and increases as they get further apart. So it increases close to 0. And then we can read this part, which says, work must be done against the attractive forces to separate neighboring atoms. So this is the main point that we're trying to learn here for this topic, which is basically that you need to put in work to make something expand because they need to do work against these bonds. So essentially what I'm trying to say is and this is super simple science, when something comes from a liquid and then they evaporate into a gas, the molecules that are inside the substance, they have to separate by a great amount when you change into this. What this means is that the molecules, their separation will increase. So basically, in order to change a liquid into a gas, you need to put in work so that its potential energy can increase. Now, potential energy has nothing to do with temperature. Remember that kinetic energy is something that determines the temperature, and that's not potential energy. So this is the whole reason why when something cools down, as we saw earlier, it has this sort of curved shape, right? Over here, we said that it was freezing. Well, basically, this was when a change of state was happening. So we can actually kind of look at this a bit clearer when we look at how we heat ice, and that's a very basic example. So let's have this sort of 3 ice cubes and we're going to supply energy to it. Let's assume that energy is supplied to the ice at a constant rate. So we decide to graph temperature against time, and this is the sort of thing we're going to see. Now, the melting point of water is going to be at 100 degrees Celsius, or this is also the boiling point of water, obviously. And the freezing point of water is going to be at 0 degrees Celsius. Oh, hold on, this is the melting point. Melting point or freezing point. And this is going to be evaporation or condensation, boiling or condensation point. Or condensation. So you can see that very clearly right here. Here we have the freezing point, here we have the boiling point, 0 degrees, 100 degrees. And at each of these points where a change in state is supposed to happen, we see a flat curve for a while. We see a very flat line. And why is that so? Well, when temperature is changing, we can assume that the energy that is being supplied to the ice is being translated into kinetic energy of the water molecules. The water molecules are going to vibrate faster and faster, and that's why their temperature is going to increase. But there's not a big difference in the size or the volume of the ice when it's becoming colder ice to a bit of a warmer ice. For example, negative 20 degrees ice to negative 5 degrees ice. It doesn't grow bigger by a huge amount. It doesn't expand that much. And what that means is that nearly no energy is being supplied so that it's doing work against the forces, the attractive forces. Not a lot of change happens to the potential energy of the ice. However, now the ice melts at its freezing point, right, or its melting point. That's when no temperature change occurs, which means that even though the energy is constantly being supplied, like we didn't turn off this fire right here, the energy is being used for something other than kinetic energy, and that is being used to overcome the forces that are holding this ice apart and basically doing what we learned earlier, which is it's going to do work so that its potential energy, its electrical potential energy of the molecules are going to be increasing and becoming closer to zero. So that's what happens here, and that's also what happens here. So we can read the two statements. It says, when temperature increases, kinetic energy of the molecules increases. If the molecules break free of their neighbors and become more disordered, their electrical potential energy has also increased. So this is basically what the graph was again. And we can take a look at this. This is the boiling point, 100 degrees Celsius. At 100 degrees Celsius, you see that it takes much longer. This period of changing state takes much longer than this period. And that's because the specific latent heat of vaporization. So remember, specific latent heat is how much heat is required to change the state of a certain matter without changing its temperature. Now, that amount for the melting point as well as the boiling point, they're actually different. And for most substances, to boil a certain subject, you need to put so much more energy than to melt it. And that's why you take so much longer, because you need to put in more energy for something to break bonds completely. Because you might have known that the molecules in a liquid, they are actually still touching. Maybe they have a little bit of a gap once in a while, but a lot of them are still touching. They're kind of sliding against each other. Whereas after you become a gas, you barely actually have any sort of contact or influence over one another. And that's why you need to break more bonds. You need to break all of your bonds in a gaseous state rather than in a liquid where you maybe only need to break one bond per molecule. And it's also very useful to note that in a gaseous state, the potential energy is very, very close to zero, if not zero. Why is that so? Because the gases are really far away from each other when they're in the gaseous state. And if you relate that to how small the molecules actually are, the forces that they exert on each other are very close to zero, and therefore their potential energy is also very close to zero, if not zero. Lastly, I just want to say how we can also interpret this for evaporation. So evaporation is when a liquid changes into a gas without boiling. And what happens here is that the energy or the kinetic energy goes down when something evaporates. This is liquid inside a jar. Why is that so? It's because the more energetic, and I mean the more kinetic energy sort of molecules, tend to have the ability to escape them altogether, and they have the energy to kind of overcome the potential and the intermolecular forces and leave, which leaves everyone else with an average lower energy, because this is an above average energy molecule. The rest, obviously, they're going to be left with a slightly below average energy. So that's why evaporation leads to cooling, and that's why we sweat, etc. And we can also say that it goes down because there is a net outflow of energetic molecules. So that's about it for how to classify these sorts of things. I hope it helped, and you can check out my other videos on physics as well. Thank you.